On February 21st, 1969, the Soviet Union set a record for the world's most powerful rocket to fly, a title that they would hold on to for over 50 years. But on April 20th, 2023, that record would finally be broken by SpaceX's Starship and its super heavy booster. People have been quick to point out the similarities between these two rockets, most notably the ridiculous amount of engines on the first stage of each rocket. The N1 featured 30 NK-15 engines on its first stage, while Starship's super heavy booster sports 33 Raptor 2 engines. But the similarities don't end there. In fact, the first integrated launch of Starship proved the rocket to be even more similar to the N1 than most would be comfortable with, considering the N1 flew 4 times but never made it all the way through the first stage burn. And this has brought up an all-important question. Has SpaceX fallen into a similarly flawed design that plagued the N1? Why did they choose so many engines? Will it continue to suffer a similar fate over and over like the N1? Or is there something inherently different? My name's Tim Dodd, the Everyday Astronaut, and today we're going to answer these questions and compare the most powerful rockets ever made from completely different sides of the world and totally different eras to figure out how they're similar and perhaps more importantly, how they're different. And like always, here's the timestamps for this video. The YouTube timeline is broken up into these sections, and we have an article version of this video up at everydayastronaut.com for links and sources. Okay, N1 versus Starship. Let's get started.
3, 2, 1,
That's one small step for man. Contact with a test 1.
Okay, let's start off by comparing these two vehicles side by side. I've talked about each of these vehicles pretty extensively in previous videos, such as Starship versus Falcon 9 and my entire history of Soviet rocket engines video, but I've never actually directly compared them before. The N1 was the Soviet Union's attempt at a moon rocket, a rocket that would nearly match the capabilities of the United States' incredible Saturn V rocket. It was massive. At the base, it was a ridiculous 17 meters wide, and it tapered up to a point with the upper stages that were about 6 meters in width. It stood an impressive 105 meters tall, and fully fueled, it weighed a total of 2,735 metric tons. SpaceX's Starship, on the other hand, is even more of a skyscraper. It's 9 meters wide on both stages and comes in at 120 meters tall. But where Starship's numbers get shocking is with its weight. When it's fully fueled, it's about 5,000 metric tons, so almost twice as heavy as the N1. The N1 was capable of putting 95 tons into low Earth orbit, while Starship is designed to be able to take up to 150 tons into low Earth orbit. And it does so while being fully reusable. But what's even more ridiculous is it can put around 300 metric tons into orbit if it's not fully reused. This puts both rockets squarely in the super heavy lift category, with Starship being the most capable rocket ever built. Each rocket utilized different propellants. The N1 was powered by Kerolox, specifically RG1 and liquid oxygen. Starship, on the other hand, uses Methalox, so liquid methane and liquid oxygen. The N1 had a lot of stages. The rocket had a minimum of 3 stages, but when sending a payload to the moon, it would have utilized up to 5 stages, in a similar fashion to the Saturn V with the Apollo service module and the lander stages, and of course the entire rocket was expended. Starship, on the other hand, is only a 2-stage rocket. And again, perhaps most importantly, both the massive super heavy booster stage and the Starship upper stage are designed to be fully and rapidly reusable. But perhaps the biggest thing these rockets each share is the ludicrous amount of engines, like we talked about in the intro. The N1 had 30 NK-15 engines on its Block A first stage, 8 NK-15Vs on its Block B second stage, 4 NK-19s on the Block V third stage, 1 NK-21 on the Block G fourth stage, and an RD-58 on the Block D descent stage. There's 33 Raptor 2 engines on the Super Heavy booster and 3 more sea-level Raptor 2s and 3 vacuum-optimized Raptor 2s on the Starship upper stage. But these numbers are all subject to change as Starship is still in development. The NK-15 on the Block A booster of the N1 utilized the oxygen-rich closed cycle, which those of you who have watched my deep dive on Soviet rocket engines may know this is something that the Soviets mastered in the early 60s. The engines were impressive, capable of 1,526 kilonewtons of thrust and 297 seconds of specific impulse at sea level, and it had a mass of about 1,250 kilograms. Raptor 2, on the other hand, produces 2,255 kilonewtons of thrust and 327 seconds of specific impulse at sea level, while having a mass of only 1,600 kilograms. This means the Raptor has approximately a 144-to-1 thrust-to-weight ratio, while the NK-15 had a thrust-to-weight ratio of about 125-to-1. So not only is the Raptor 2 much more efficient, it also produces more thrust kilogram for kilogram, which is important. Now we should mention that, of course, in typical SpaceX fashion, they're still upgrading Raptor, and in the relatively near future, they'll be utilizing Raptor 3, which is already producing some even more impressive numbers. So this is all subject to change, but even with Raptor 2, we can see how advanced this engine is already. So as you can see, the rockets are quite different from each other, but they do share a couple similarities, like being super heavy lift rockets and utilizing several smaller engines rather than a few bigger ones. But they actually share more in common than just their hardware. So let's dive into some core philosophies that they share, including the pros and cons of utilizing so many engines, why they both believe in testing by flying, and heavily leaning on the iterative process. So let's start off with the biggest question people have. Why do these rockets have so many engines? Doesn't more engines mean more potential points of failure and ultimately a more complicated system? Well, many less powerful engines have a few advantages over fewer, more powerful engines. Most obviously is that a loss of an engine has less of an impact on total thrust levels, with many smaller engines versus fewer larger engines. Let's look at the N1 versus the Saturn V. The N1 had 30 engines producing 45 meganewtons of thrust, whereas the Saturn V had 35 meganewtons of thrust from just 5 engines. So if you were to lose one engine on your Saturn V, you'd lose 20% of your thrust, which if early on in flight would have certainly led to a loss in mission. Whereas if you lost just one of your 30 engines, you only lose about 3% of your thrust, which is well within the margins to continue on in pretty much any situation. But as far as reliability goes, more engines also has the potential for more failure points. More moving parts, more chances for failure, more complications, and more chances that one engine's failure could affect its neighbor and cause a cascading failure scenario. So there's a little bit of a bell curve here, and definitely an engineering trade between having fewer engines because it's simpler, but it's more susceptible when there is a failure. On the other hand, more engines is more likely to have a failure, but it can be more robust when an engine does fail, and it's hopefully not as catastrophic. SpaceX's Falcon 9 rocket actually already utilizes this approach by having 9 smaller engines instead of one large engine like their biggest competitor historically, ULA's Atlas V rocket, which only has a single RD-180 engine. So how has that been going for SpaceX? Well, for the Falcon 9, in total, 2 Merlin engines have shut down on ascent, and to date, none of their failures have ever caused a loss in mission. Now, there have been 2 other losses of engines which caused the failure of a Falcon 9 to land, but that's not mission critical. So overall, a larger number of engines have helped make the Falcon 9 become one of the most reliable rockets ever made. In fact, even the landing of the Falcon 9 has become more reliable than almost any other launch of a rocket in general, with over 115 consecutive landings in a row. So SpaceX's landing of a rocket success streak is better than pretty much every other rocket's launch success streak. Think about that. And SpaceX has already taken this approach up threefold with their Falcon Heavy rocket, which uses 27 Merlin 1D engines at liftoff. And to date, that rocket has had a flawless track record for mission success. Now, there's a few things you can do to help many smaller engines be even more reliable, including having each engine inside its own blast containment shield. This way, if the engine does experience a catastrophic failure, it won't affect its neighboring engines. This is something that SpaceX has already improved upon between the first Super Heavy booster that flew, which is Booster 7, and boosters after, which have a much more robust blast containment shield on each engine. But beyond the actual operation of a rocket, many smaller engines have a few huge advantages over fewer larger engines. First off, cost. The R&D and tooling costs can be depreciated through each engine much quicker if you're making, let's say, 5 times more of something. There's economies of scale that work really well here with smaller engines when you're cranking them out almost once a day. In fact, SpaceX is already making the Raptor 2 engines for under $1 million now, and they're continually pushing to make them even less expensive. Compare that to the F1 engines that were on the Saturn V, which cost about $115 million per engine in today's dollar. So even though that engine produced 3.5 times more thrust, it was about 30 times more expensive on a dollar per kilonewton of thrust measurement. And don't even get me started on the RS-25 from the Space Shuttle and SLS. That thing is also ridiculously expensive and has even less thrust than the Raptor engine. Our numbers for the price came from a recent OIG report here, and they're actually kind of conservative, and the report even says it's likely much higher than that. So the RS-25 just really is not great from a dollar to thrust perspective. Smaller engines also don't suffer the same problems of combustion instability like larger ones do. This is where the combustion chamber is so big, different areas of the chamber can experience slightly different pressures and temperatures, and it can lead to oscillations. These small instabilities can lead to big problems, and it's combustion instability that almost grounded the Saturn V because its gargantuan F1 engines were plagued with combustion instability issues. The US figured it out, but the Soviet Union never really figured out how to solve combustion instability on large engines. Instead, it was most common for the Soviet Union to take one engine and split its combustion chamber up into 2 or 4 smaller chambers as a way to avoid combustion instability. When designing the N1, lead engineer Sergei Korolyov reached out to a new engine designer, the Kuznetsov Design Bureau, or OKB-276, and wanted smaller engines to avoid combustion instability. Another advantage of smaller engines is they're just easier to handle, test, install, and move around in general. We see SpaceX moving Raptors around all the time like it's nothing down at Starbase and at McGregor. Being smaller and easier to handle ends up being an efficiency in time and labor hours. It's easy to imagine that it's a lot easier to install an engine like Raptor that can be installed in hours versus an entire F1 engine on the Saturn V, which would have taken days and huge machinery to install. But high production rates also help find flaws in design and production much quicker. If you have, let's say, 5 times more engines than another design that has fewer engines, that's 5 times more opportunities to find flaws or make improvements in manufacturing. This also applies to testing. If each engine goes through a similar testing phase, you'll rack up 5 times more test stand time in total with several smaller engines, which will lead to a better understanding of the system and a more reliable engine in the long run. This means 5 times more startups and shutdown sequences. It means there's more time to really hone in what works and what doesn't work. Stoke Space CEO Andy Lapsa brought this concept up to me when talking about their unique test engine that has 15 combustion chambers, drilling in the advantage of testing so many combustion chambers.
Every single test we're doing tests 15 of these systems at once. We're racking up, like if you rack up chamber test time, we rack that up
15 times faster than a normal program. And that could be seen as a totally bad thing, but at the end of the day,
at the end of the day, it's got to work, right?
Yeah.
Like, look at Starship. It's got a gazillion engines, right?
Yeah.
And if you beat the crap out of these things enough, then you work all the bugs out and they're reliable.
Yeah.
Now, of course, it might be easy to point to the first flight of Starship in 2023 and say, well, it doesn't look like those Raptors were all that reliable after all, were they? But let's not forget, those were literally some of the first Raptor 2 engines ever made. As of the making of this video, SpaceX now has produced over 300 Raptor engines and have developed a much more robust testing regime for each engine, which will hopefully lead to outstanding reliability. I don't think it'll be nearly as much of an issue on later Super Heavy rockets. But at the end of the day, SpaceX still decided to fly Booster 7, despite knowing it had a relatively low chance of success. Why? Why did they do that? And why did the Soviets do something similar with the N1? Well, here's the thing. The Soviet Union didn't actually have much of a choice in the matter other than to just fly the N1. The N1 not only couldn't static fire test the whole Block A first stage on a stand or at the launch pad, but they couldn't even test fire each individual engine. The N1s that flew all utilized the NK-15 engine. One flaw it had was it relied on pyrotechnics to open valves. This means they were single-use and required a massive overhaul to fire again. So instead, the Soviets decided to test just one in every 6 engines that came off the manufacturing line to try and test for general errors in production. Now, as you can imagine, this means the engines flown on these flights weren't actually test-fired before being lit for liftoff. So yeah, this means the only way to actually test the N1 at all was to just launch it. And this is exactly what the Soviet Union did all 4 times, and again, never getting all the way through the first stage burn. Just send it is the common philosophy that both the Soviets and SpaceX have adopted. So why did SpaceX choose a similar philosophy and just fly Starship? Isn't it different with SpaceX, who does test every single engine, and they even performed a handful of static fire tests with the booster and Starship upper stage? Well, SpaceX still believes the best way to gather data and to get to the next step is to test. Even if the test fails, there's still a lot to learn. So instead of trying to completely solve the complex problem of flying, landing, and reusing the world's largest rocket, just start by trying it and seeing what goes wrong and what goes right. The goal of the first Starship integrated flight test was to clear the launch pad and not blow it up. Now, although the rocket cleared the launch pad, a large amount of concrete was violently ejected from below the pad and tore up a good amount of the area. But I think that's just going to be a small blip in history, and 2 years after the making of this video, no one's going to be thinking much about the concrete ejection problem from the first launch. But the first test flight did validate many things. The rocket made it through the point of maximum aerodynamic pressure, or max Q. It put the heat shield tiles through some pretty strong high velocity airflow. It validated aerodynamic models and guidance and control. It also proved the launch pad and systems, including the tank farm, the pumps, the coolers, the quick disconnects, and the launch clamps, all worked as designed. They got real world experience from flying. So overall, SpaceX validated many things and even learned the rocket was perhaps a bit too robust and maybe had too small of a flight termination system, since the flight termination system failed to immediately destroy the rocket when it was activated. And in my opinion, the fact that the flight termination system didn't immediately destroy the rocket was by far the biggest failure of the first flight test. Everything else, including the concrete tornado, actually went better than expected and was still largely considered a success. But this still all raises the question of why did SpaceX and the Soviet Union do this iterative design process instead of just doing it quote unquote right? And just engineer and test every part until it's pretty much perfect and you have a high degree of success for that first flight. Well, let's take a look at NASA's SLS rocket. It took 12 years to go from signed legislation to flight. But SLS had to work perfectly or else it was at risk of cancellation. So things were tested, engineered, and worked out to a high degree of likelihood of success, which it nailed. Now, granted, it cost billions of dollars per launch vehicle and has cost over $30 billion to get to the first launch of SLS and Orion, but it does just go to show how important it was that it all worked flawlessly on that first launch. Now, Starship, on the other hand, began engine development in 2016, and around that same time, it became a legitimate project. So it took 7 years before the first integrated flight test, and it didn't complete all the milestones, and the rocket is still far from being operational. But we can imagine where the program will be in 5 years. Likely by then, it will be more operational, at least to the point of flying some tankers and payloads like Starlink, and hopefully even NASA's HLS Moonlander variant. And from there, the rapid production rate and the evolution of the rocket means it will only continue to become more capable and more reliable. And again, we're already seeing some details about an upcoming Raptor 3 engine. So everything we've talked about is likely to be outdated sooner rather than later. And I expect that the 10th Starship that will fly will look quite different and will be a lot higher quality than anything we've seen to date, which is something that is harder for SLS to do because it doesn't have the freedom of failing or rapidly making changes in design. So SpaceX is following in the footsteps of the Soviet Union by build fast, test, break stuff, iterate, fly, blow stuff up, learn from it, repeat. But will Starship ultimately suffer a similar fate as the N1? Well, now it's time for my final thoughts on whether or not I think Starship might repeat history. So why did the N1 fail, and is Starship doomed to do the same thing? Is there just simply such a thing as too big, too powerful, too many engines, and engineering too fast? I think the biggest misconception is that the N1 failed simply because it had so many engines. While in some ways, of course, it was a contributing factor, it's not really the full story. The main reason the engines on the N1 failed wasn't because of quantity, but quality. The NK-15s flown on the N1 were extremely primitive, and as we know, they were still relatively untested and quite failure prone. Couple of these relatively new engines that couldn't be tested, a full first stage that couldn't be tested without flying it, and then a primitive computer called Cord that was in charge of managing that many engines. It was a recipe for disaster. Not to mention, the N1 also steered via a pretty advanced mode of steering known as thrust differential. Thrust differential is where you throttle engines to provide pitch or yaw. So increase thrust on one side and decrease the thrust on the engines on the opposite side, and it will pitch or yaw the vehicle over. This means the engines need to handle precise throttle commands, and they spend more time in transients as they throttle up and down. This is a fairly advanced task, even for today's rockets with modern computers. A major downside to relying on thrust differential is that if an engine shuts down, the Cord computer had to shut down the engine opposite of it so as to maintain equal thrust. The N1 could fly nominally with 4 engines shut down, but that actually means they could only lose 2 engines, since each engine that would shut down would require the shutdown of its opposite engine. So there wasn't actually much room for error. Starship's Super Heavy booster, on the other hand, primarily steers via the center 13 engines that all gimbal. Now, gimbling is where the engine itself can swivel and provide pitch and yaw. And assuming there's at least 2 engines, they can even provide roll control that way too. The Raptor 2 has an astonishing gimbal range of 15 degrees. This is the most gimbal range of any main engine, at least that I know of. And they can do so at extremely ridiculous rates with the new electromechanical servo thrust vector control system that will be on all Raptor 2s after the inaugural launch. And that's actually something that was different about the first flight test of Starship. The older Raptor 2s were hydraulically driven for their thrust vector control system for the gimbals, and those also had to rely on some hydraulic power units, or HPUs, and those failed on that flight test. But now with the electromechanical thrust vector control system, they won't have to worry about that at all. But having engines that gimbal also means that Starship doesn't need to shut down opposite pairs to maintain control. The rocket can simply use the gimbals to correct for any offset in thrust if an engine does fail. We actually saw this in action on the first flight test with Starship, where the rocket lost many engines, but it maintained control via gimbling, and it didn't need to shut down opposing pairs. Now, personally, I honestly have no doubt that had the N1 been able to continue flying, they would have easily figured it out, and likely within the next flight or two, and especially because the next N1, called the N1F, would have had much upgraded and much more reliable NK-33 engines. Another thing to remember is that Starship has had over 50 years of computer and aerospace advancements to lean on, which I don't think I need to really even begin to explain how much computers and aerospace has advanced in 50 years. In fact, thanks to modern computers, the engines can be less prone to catastrophic failures because the engines can sense when things are off nominal and they can quickly shut things down before they get worse. But in the end, I think one of the biggest reasons the N1 failed altogether and never got those additional flights is the untimely and the unfortunate death of lead engineer Sergei Korolyov, who died right in the middle of development in 1966. And unfortunately for the program, Korolyov was the main advocate of the program, while his contemporaries, Valentin Glushko and Mikhail Yangel, had other plans and they just weren't supportive of the N1. Not to mention the program was underfunded to begin with, and after Korolyov's death, and then of course with the Soviet Union being defeated by the United States' Apollo program to the moon, the N1 was canceled before it ever got a chance to really mature and live out its ultimate goal of sending humans to the moon. Now, isn't SpaceX still susceptible to running out of money? Or what if there is an untimely death of Elon Musk? Or what if they just end up canceling Starship altogether? Now, in my opinion, at this point, I genuinely don't see much risk of that happening. Not only has NASA invested billions of dollars into Starship, because they're going to be using Starship as the lunar lander for the Artemis program, but SpaceX has a solid revenue stream by not only being one of the most prolific launch providers by a huge margin, they also are likely operating at the highest profit margins by reusing their Falcon 9 boosters and fairings, but they are also quickly becoming one of the largest internet providers. SpaceX is investing billions of dollars into making Starship happen, and not just make it happen once, but they're literally mass producing Starship. Although the N1 was set up in a similar fashion with a production rate of up to 1 N1 a month, and they had engines coming out once every 1.5 days or so, there really hasn't ever been a rocket engine built like Raptor, which is being built so inexpensively and so often, and they're still pushing that envelope. SpaceX is currently building multiple facilities to build Starships at scale. Now they're baking in efficiencies to maximize economies of scale, the iterative design process, and of course, this is, after all, a reusable launch vehicle that once it's proven, it will be beyond disruptive. It'll be transformative. Much of what I just said can be backed up by the fact that there's already several vehicles mostly finished just waiting to fly. Now, granted, they currently don't have a launch pad to launch on as of the making of this video, but I think SpaceX can get that part figured out, no problem. Now, I know it's easy to write me off as just a SpaceX fanboy that's gonna think that Starship's gonna work out no matter what and not fall to the same fate as the N1. But don't forget, over and over, SpaceX has proven to be able to do what was once thought impossible, and every time the impossible becomes routine in about a year. I mean, just look at the Falcon 9. First, just launching was considered impossible, then they did it. You know, getting to the International Space Station was something they would never be able to do. They did that, no problem. Then they started working on landing the rocket, and people said that was impossible. Well, they did, and then people were like, okay, cool, party trick, but you're never gonna be able to reuse that thing. They did. And they're like, okay, sure, maybe you'll reuse it once or twice, but you'll never reuse these things over and over. It'll never be financially worth it. Now they are up to like 15 reuses on most of their fleet. Their fleet is just getting so ridiculous. They're so used, it's really rare to see one that's new, or it's really rare to see one expended or one that doesn't land. I mean, that's just almost unheard of these days. What about fairings? Those were supposed to be impossible and not worth it to reuse, and now it's rare to see a new set of fairings. And humans, let's not forget about humans. People thought there's no way SpaceX would get humans into orbit. They just thought it was something that would never happen. Of course, as we know now, they're the most prolific provider of getting humans into orbit. Not only for NASA getting to the International Space Station, but also private individuals doing free flights and things. I mean, it's just incredible. And all of these things have had people the whole time saying, this is impossible, it'll never happen, and now so many of these things are completely routine. Now, of course, it's really hard to predict when Starship will go from completely impossible and experimental to completely ordinary and routine and mundane, but of course, still game-changing. So what do you think? Do you think Starship will suffer a similar fate like N1? Do you think we'll ever see a completed first stage burn and a full clean stage separation? Do you think we'll see it get to orbit or do all the other things it's supposed to do and become operational? Will it take a year, 2 years, 5 years, 10 years? Never? Let me know your thoughts in the comments below, and don't hesitate to ask any additional questions. I'll get to as many of them as I can. I owe a huge thank you to my Patreon supporters and my YouTube members for helping make all of this stuff possible. If you want to join our amazing community, get access to some exclusive live streams or other things like our Discord channel, or even previews of these videos before they come out where you can find errors or give your thoughts and opinions, head on over to patreon.com/everydayastronaut or click the join button below here on YouTube if you want to become a YouTube member. And while you're online, be sure and head on over to our web store for shirts like this, the Aerospike t-shirt, or our incredible 1/100 scale Falcon 9 model rocket that, it's pretty amazing. These are made out of metal. They're extremely high quality. I think it's one of the most detailed rockets you'll find, period. These are incredible display pieces. We have lots of other fun stuff like our dress wear, our schematics collection, and fun accessories like this amazing color-changing heat shield mug. Head on over to everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.